Welcome back to multivariate calculus. In this video, we're going to start our exploration of three-dimensional space. For this video, I am not mirroring myself for the first time, which makes it very difficult for me to actually gesture at things behind me. But I'm going to also be doing a lot of gesturing with my right hand, which I want to make sure that you are able to follow. And I'm not skilled enough to make the same gestures with my left hand, and mirroring it would make it look like my right hand is my left hand, so it would just be a mess all around. But the orientation of axes in three dimensions follows what's known as the right-hand rule. To understand the right-hand rule, take your right hand and extend your pointer finger straight up, your middle finger kind of sticking out of your hand, and your thumb straight up like you're giving a thumbs up, but you're holding your fingers weird for some unknown reason. And what I want you to notice is that I can orient my hand so that Z is pointing in the direction of my thumb. So my thumb is Z. Y is pointing in the direction of my middle finger, so my middle finger is Y. And X is pointing in the direction of my pointer finger, so my pointer finger is X. That orientation of X, Y, and Z is called the right-hand orientation for obvious reasons. The right-hand orientation was developed at a time in the European society where people who were left-handed were locked in dungeons and accused of being possessed by demons. So anyone here who is left-handed, unfortunately, the right-hand rule is right-hand centric because it was developed at a time when being a lefty was synonymous with being evil and not to be trusted and locked away and kept from polite society. Aren't you glad that society has changed? But anyway, this orientation of right-hand rule, traditionally we set up our axes looking like this, where the plane of the board or the screen or whatever it is you're drawing on is the YZ plane, and then sticking out from the YZ plane towards you is the X-axis. We can rotate this in any direction alternate to that, but that is the orientation that we are thinking about and that we're focused on. To try to make sense of what we're looking at, let's jump over here to Geogebra, and you can see that I have plotted a particular point. I'm going to talk more about that point in just a few moments, but it's floating there in space, right here. And what I want you to immediately notice about Geogebra is that the axes, I actually have color inverted, so you're seeing cyan, magenta, and yellow for X, Y, and Z. When you're in GeoGebra, it's a blindingly white screen, and the X-axis is green, the Y-axis is red, the Z-axis is blue, or maybe not because I'm colorblind. But you'll notice here that instead of coming out towards you, the X-axis is floating off to the side, and the positive Y-axis is pointed away from you. So if I go ahead and get my head out of the way, one of the nice things about GeoGebra is you can actually just click anywhere and drag to rotate the axes around to be in an orientation more like what you were trying to draw. And so let's take a look at doing exactly this, where notice the positive X-axis. I am rotating until I am looking right down the barrel of the positive X-axis, or pretty close to right down the barrel of the positive X-axis. And when I do that, the Y and Z axes form a plane, and you can't even see the X-axis because you are staring right down the barrel of it. If you play around in the settings menu, it takes a while and I don't think it's very interesting to watch, you can actually cut off the axes so you're only seeing the positive version, and that's more like what we drew. And then instead of focusing right down the X-axis like we are here, the way we draw things by hand, generally what I want you to think of is that we're trying to focus at a point somewhere in the yz plane for positive y, positive z. Maybe point P, maybe somewhere near there, but that causes the x-axis, instead of going right into your eye, to shoot past your head and gives us the version of this that we drew when we set it up by hand. But we can change the orientation of our axes. We don't have to have the z-axis pointing upward. Sometimes the y-axis pointing upward makes more sense. And that's actually something that Geogebra can do pretty readily in its settings. So we can set this thing up so that we are looking at the XY plane, looking down the barrel of the Z-axis. And notice here that X and Y kind of look more how you like, or how you're used to from graphing two-dimensional things, and now Z is pointing right towards you. And if I go into my settings and turn off positive direction only for each of the axes, we can play around a little bit with, what the negative z-axis looks like and kind of move things around. But again, if you're looking right down the barrel of the z-axis from the positive direction, then the thing that you have really is the xy plane. All right. GeoGebra has options for z being the vertical direction. It also has y is vertical as an option. It unfortunately doesn't have an x is optional or x is vertical option, but if you use the right-hand rule, you can figure that out. So if I jump back here and I go back to my hand, again, remember x, y, z, and if I want to set this up so that x is vertical, it looks like y is going to be coming towards you and z is going to be going off to the side. So x is vertical, y is coming towards you, z is off to the side, is another option of an orientation for setting things up. Right? The other thing that we saw looking at this was the ability to look at projections. If we set up x and y, we had z coming right towards us. If we set up y and z, then we have x coming right towards us. And if we set up z and x, then we have y coming right towards us. This is the way that I like to think about projections, and it certainly works in a lot of cases, but not quite in all of them. So there's another option on how to set up projections. Instead of rotating around so that x and y positive, y and z positive, z and x positive are always in the first quadrant, sometimes it's useful to look at the general orientation of the axes as your guide. Right? X is down and to the left, y is to the right, and z is up. And so there is another rule of thumb that says, let's rotate these around so that we always can graph with z up, y to the right. And if we want to make sure that y is to the right, then that would make x down. And if we want to make sure that z is up, then that would make x over here go to the left, right? Again, in the original three-dimensional axes that we drew, x was kind of down and to the left. So that's why it ends up down, it ends up to the left, and it seems like it can't make up its mind. But notice here, the challenge of this is that the positive quadrant moves around depending on which projection you choose to use. Both of these are very commonly used tools for graphing. You will see figures that use these several places in the course. I'm going to try to use both of them so you get familiar with both options. But they are a tool and they certainly can come to use. While we're talking about projections, I want to again talk about the right-hand rule, right? You can think about x, y, and z as being cyclic. X, y, y, z, z, x. So if you take your right hand and thumb up, place it on the page, your fingers will naturally curl in the shortest path from x to y, whether that's like this up on this one, so from x to y, or down here from x to y when your thumb is sticking out of the page. Likewise, from y to z, from y to z, and from z to x down here behind me, where I can't really get my hand to work that way, right? From z to x up here, from z to x, or down here from z to x, kind of like that, right? Breaking your wrist trying to make sure that these things start to make sense to you. In courses that handle things in 3 dimensions, which are predominantly Calculus 3 and physics courses that talk a lot about electricity and magnetism, it's always hilarious to sit and watch the class because everybody is breaking their wrist trying to make sure that they set everything up correctly following the right-hand rule. All right. So we have projections, we have the axes themselves. I'm going to go ahead and flip myself back to mirror mode because I don't actually need to wave my right hand around anymore today. And actually, let's just get my head out of the way and take a look at a specific example of that point that we were plotting. All right, here we go. Nice fresh set of coordinate axes. And now that we have talked a lot about the coordinate axes, I guess it's time for me to give a formal definition. Just like we defined the coordinate plane as R subscript or superscript 2 as the set of all ordered pairs x, y, such that x and y are real numbers, we can define the Cartesian product R3 as the set of all ordered triples x, y, z, such that x, y, and z are all real numbers. So if I have a point P defined as 1, 2, 3, I can put some tick marks on my axes, and we'll pretend that these are all equally spaced. Again, I'm drawing this by hand, so I don't have high hopes for that actually having happened. And here's my trick. I look for, the same way you do in 2 dimensions, I look for x equals 1, I look for y equals 2, and I look for z equals 3. Once you get used to this, you don't keep marking those places on the axes. Just like when you first learned to graph things in 2 dimensions, you marked the coordinates on the x and y axis, and then you very quickly stopped doing that. And then you draw your dashed lines. Although in 3 dimensions, drawing the dashed lines is a little bit more challenging. So I draw a line in the xy plane where x is equal to 1, and in the xy plane where y is equal to 2. And notice that the y line is kind of at an angle so that it's parallel to the x-axis. All right, but that gives me the point here, which is going to be the point 1, 2, 0, the projection below 1, 2, 3 in the xy plane. And so to get to the z coordinate, I'm going to have to go upward from that point. Now, how to get z is where things get a little bit tricky. Right? Notice that in the xy plane, that's terrible. Let's try that again in a way that's actually a straight line. In the xy plane, notice that the line from the origin to the point in question is at this kind of slope. When I draw my line from the z-axis to my vertical line, I want to follow the same slope. I want to draw something parallel to that, which gives me the point right here. To make it make sense when I draw things by hand, I don't draw out all of this, but I do draw the dashed lines in the xy plane and going up and going to the z-axis from there. So those lines are what I draw. All the white lines is more than what I draw, but try to hopefully gives you some idea of how that's supposed to work. All right, so if I paste in a new set of axes and I look at another point, we could draw multiple points in the same axes, but that's really messy. All right, let's look at point Q, which is 3, 1, 2. And we'll play the same game, only this time I'm not going to draw in all of the detail. I've got y equals 1 and x equals 3, which kind of meet about there. And kind of tracing what that angle looks like, I have an angle that kind of does something like that to match it. And we can drop down. And there's my point Q. Right. Once again, you can also use computer software like Geogebra. Here I've already plotted point P. I can go in and just type in my other point, Q equals 3, 1, 2. Get those both labeled. And again, click and drag until I can get these oriented in a way that kind of makes sense for what I'm doing. Another really nice trick, it's difficult to print this way if you're asked to submit a file, but if you're trying to figure out what's going on, if you click and drag horizontally, very often, not always, but very often you can get GeoGebra to start spinning the axes around to give you a three-dimensional view of what's happening to these points and where they relate to each other. Sometimes I find that doing that makes it a lot easier to see what's happening. Sometimes I find that it just makes me dizzy. Now that we're somewhat familiar with the coordinate space, let's get rid of these points. And the other thing that I want to think about is what a vector looks like in 3 dimensions. There are several different notations for 3-dimensional vectors. GeoGebra gives us one that we're not going to focus too much on, but we'll spend a lot of time on. Anyone who is going on to take a course in linear algebra, or if you've already studied linear algebra, you already have seen this notation. But very interestingly, if you name your variable with a lowercase letter in GeoGebra, it will interpret that you want a vector with those components rather than just the point. If you use a capital letter, GeoGebra interprets point. If you use a lowercase letter, GeoGebra interprets vector. All right, so if I want the vector 3, 1, 2, and let's change the color because that's really challenging to see. Go into settings here, go into color, and choose something that is going to very much stand out. We don't have any bright blue, so let's go with that. That doesn't look bright blue at all, but okay. Um, let's try that one more time. I might have just clicked the wrong button. And maybe this blue will be a little bit easier to see. Yeah, I think that stands out from what we had otherwise. Right. But if I move around here, I can see that it has drawn the vector going from the origin to the point 312. Right? We had called that point Q. I can put that back in. Right, so we have a vector going from the origin to point Q, and we can see what that looks like. Right, so vectors in 3 dimensions work very much the same way as vectors in 2 dimensions. We have a couple of different notations for them. If I jump back over to my notes sheet, I can start talking about vectors algebraically instead. All right, so we can name the components in component form like this. We can also use unit vector notation. The vector in the x component is still called I hat. The vector in the y component is still called j hat. And then I suppose it makes sense that if you're going to continue onward, the vector in the z direction is going to be known as k hat, following the alphabet. And we can, when we have vectors in component form, we can perform vector addition the same way we have before. So if I have vector v is 312, and I have vector u as, say, 2, -4, 1, and I want to add u plus v, I will add them component by component. 3 plus 2 is 5. 1 plus -4 is -3. 2 plus 1 is 3. And if we take a look in Geogebra, setting up vectors is sometimes a little bit challenging, but let's get, actually we need these. We've got the point 312, the vector 312. We also had vector u, which was 2, come on, 2, -4, 1. And when we added those together, first of all, trying to get an orientation where we can follow and see what's happening here. When we added those together, we ended up at a point which was 5, -3, 3, and let's call that vector w, which goes to the point 5, -3, 3. And once again, I can spin around a little bit to try to see what's happening and try to find a good orientation to show this off. If I take my vector 2, 4, 1, it is in fact exactly the vector that goes from Q to R. Right, the vector from Q to R is in fact the vector 2, -4, 1, just shifted over to somewhere else. So you can think about adding vectors in the same head-tail graphics that you've seen before. It's just that drawing head-tail graphics in 3 dimensions is very challenging, which is why we are much happier with the um, algebraic notation. Graphing things in 3 dimensions works. You can figure it out. It is very challenging. I don't like doing it. I avoid it whenever possible. And I will stick to writing things out in this form. The other thing we talked about with vectors in the plane is calculating the norm of the vector or the magnitude of the vector. And let's take a generic vector with x I hat plus y j hat plus z k hat. And to take the norm, you took the square root of the squares of the components, x squared plus y squared. I claim that if we want 3 dimensions, we just add in a z squared, and that's all it is. Technically speaking, that's actually the definition, and everything else falls in place from that. But I'm going to try to draw this. I'm going to do a very bad job, but I'm going to try my best. And I'm going to draw it in a different way than we have represented things in space so far. I'm going to draw it by first drawing a rectangular prism that looks something sort of like this. Because if I set up this rectangular prism so that my lengths are x, y, and z, then my vector in question is just the vector that goes from this corner to that corner. And what I want to do is look at this thing, look at the shadow in the bottom of it, the xy plane, and recognize that if you swing the orientation around a little bit, this is a right triangle. This side over on the side is already labeled as z, but in the bottom, the length of that thing is going to be the square root of x squared plus y squared. Let's write that where you can actually read what it says. Right, the length of that thing is the square root of x squared plus y squared. And then now you have a right triangle who has sides, root x squared plus y squared, and z. And if you calculate the length of the hypotenuse, you get root x squared plus y squared plus z squared. I'm not going to go through all of the algebra. It's kind of an interesting idea. Excuse me. It's kind of an interesting idea that takes more of staring at this and trying to see what it looks like than anything else. So take some time, try to visualize, try to graph it if you need to, um, to convince yourself that yes, if we have a rectangular prism, if we have a box and we have x, y, and z labeled like this, and we draw that line across the bottom, it has length root x squared plus y squared, and then convince yourself that that gives you another right triangle, and convince yourself that the root of the rest of that thing is x squared plus y squared plus z squared to get the length of the yellow line. All right. So here's something I would like you to try. Find the magnitude of vector u, which is 4i plus 7j minus 4k. That's something that we haven't directly talked about, but given everything that I've just discussed, you should be able to figure it out. And then, thinking back to what we've done with vectors previously, I would like you to try to find a unit vector which points in the direction of this vector u whose magnitude I'm asking you to find. All right, so there's two problems for you to take a look at. See what you can do with them, and I'll see you in the next video.